Okay, so yeah, this is going to be a bit of a brief overview of the CIS data products from ISAT-2. So I'm Alec. I'm a CI scientist at NASA Goddard Space Flight Center, and I'm part of the ISAT-2 Project Science Office. So I'm involved with evaluating and hopefully trying to improve some of the CIS data products. Yeah, quick shout out to Marco Bagnardi. He's also part of the ISAT-2 Project Science Office. He's helped me with some of the slides that I'll be showing today and a lot of the evaluations that we've done. And also Ellen Buckley. So she's actually going to be leading the CIS tutorials on Tuesday. Yeah, the tutorials will give much more of a kind of in-depth overview as to how we go from some of the lower level ATL3 products to the higher level CIS products, kind of building on some of the notebooks that we had last year. And I think I'll be coming in at the end of that tutorial to talk a bit about freeboard and how we can derive CIS thickness as well. I'm not sure if Ellen wants me to shout this out, but the CIS tutorial notebooks are available on the GitHub now. So if you want to take a sneak peek before then, I think you can do so.
Yeah, but they'll be updated by the time we do the tutorial. So just be ready to re-download them.
Some frantic last minute changes, but nothing huge, I don't think. Okay, so you guys have already had a pretty great background as to ISAT-2, but just to familiarize ourselves, this is ISAT-2 in orbit on the left, and on the bottom right is this novel 6-beam configuration. So for CIS, we need to consider the fact it is 6 beams. So we have these 6 beam pairs separated by 3 kilometers across track, 2.5 kilometers along track, a weak and a strong beam separated by 90 meters. Yeah, for a lot of the work we do, we've tended to focus on the strong beam, but the weak beam has been of use to us just in terms of evaluating the strong beam kind of quality assessments as well. But we're still trying to figure out how exactly to utilize the merits of having this kind of 6-beam configuration in a strong and a weak. So hopefully that's something that can come out of the hack week too. For CIS, we're really interested in these 3 products, ATL3, ATL7, and 10. ATL3 is obviously the kind of meat with which the higher level products are derived. ATL7 is the along track CIS height and classification, and ATL10 is the along track freeboard. ATL7 also utilizes the ATL9 atmosphere product, which I probably know less about than I should, but it is a key input to especially some of the filtering that goes on with deriving those higher level CIS data. 2 other products you might have heard about, ATL20 and ATL21. These aren't available yet, unfortunately, but they should be with us shortly. They're simply just gridded versions of those same along track products. So gridded freeboard and gridded sea surface data, gridded to eventually the 25 kilometer polar stereographic grid that a lot of you are familiar with. So they're on their way and should be with the NSIDC shortly, especially the freeboard product, which has already been tested. The other thing to consider is releases. So I think this has already been touched on a little bit in terms of the release schedule, and that might be in some of the presentations you've already seen. But yeah, we're at this kind of interesting time right now in between releases, release 2 and 3. The release 3 CIS data is lagging a little bit behind because we found some funky things in the data that we had to take a bit more of a closer look at. So unfortunately, that wasn't finalized before this hack week. So all the data that you'll be working with will be release 2. The release schedule has been generally on this kind of every 6-month basis right now as algorithm improvements are made and improvements to things like geolocation. The difference between release 1 and release 2 for CIS wasn't very big. It was mainly downstream changes to the ATL3 product and slight improvements in the geolocation. Release 3 is actually involved a bit more of a improvement to the algorithm, and that's something I'm going to talk a little bit about in this talk. But yeah, there's nothing completely wrong with the release 2 data, and that's totally fine to work with. But yeah, within the next few weeks, you should start to see release 3 data available at NSIDC, and That's something to consider. I think the release 3 ATL7s might now be at NSIDC, but definitely not the 10s. So just to step through these again, yeah, you've already had some discussion of ATL3, and I know Ben will be talking about ATL3 as well, but it's really the key product from which everything else is derived. So it's the individual photon heights. So this is a nice scene of what ATL3 might look like. Each of these green dots is a given photon event detected by ATLAS. Yeah, and again, you can kind of if you just plot these scenes, you see these nice examples of where this apparent surface might be being detected by ATLAS. Again, Ellen's tutorial is going to kind of start with something like this scene and show how we can kind of go about deriving where the CI surface is and how things like clouds and background might be influencing our surface finding. The only thing I wanted to mention here was that ATL3 is challenging to work with. A lot of people think it's going to be easier than it is, but there's, for one, just a lot of data. It's a really high data volume data set, especially if you want to look at monthly or seasonal kind of timescales. There's some corrections that have been included, but not all of the corrections that we might need for CI's research. So again, it's kind of can be a non-trivial process to go from ATL3 to really doing some good CI science. And again, Ellen's going to talk about some simple tips that might help you do that. But yeah, our recommendation is often to kind of start with the higher level products, ATL7 and 10, and then maybe kind of work back to ATL3 if you need to. So these are some of the corrections that are applied to ATL3. Again, none of these are particularly CI specific or ocean specific, but yeah, the ATBD can explain those in a lot more detail. But for CIs, the key is this transition from ATL3 to ATL7, the along track CI's height and classification. And so this is the main process in terms of deriving height. So this is these are some figures taken from Ron Kwok's paper last year in JGR Oceans. And this is showing 4 example segments, height segments that have been derived from ATL3. And so the key here is that we go from individual photons to segments. And a segment is essentially an aggregation of photons along whatever beam we might be choosing. So the histograms, the gray histograms are showing binned heights from ATL3. The black line is showing a Gaussian fit to those photon distributions. And the red line is essentially just the peak of that Gaussian, so the mean. That red mean height is essentially our segment height that we produce for ATL7. So this is currently set to a default of 150 photons. That was chosen based on considerations of CI's mission requirements. So this desire to reach a precision of around 2 or 3 centimeters over CI surfaces. And I'll show another slide on that in a second. The other things to consider here is there's this fine surface filtering that's applied in ATL3, which you can kind of see by the dashed vertical lines. Again, this is an attempt to separate background photons from signal photons. You can see the trailing edge of the photon distributions, which is from the impulse response of ATLAS. And then what else? You can also see that there's different Gaussian widths, right? So the expectation is rougher surfaces cause a widening of that Gaussian. Again, that could be due to rougher sea ice, or it could be from atmospheric scattering. Yeah, okay. There are further corrections then applied to those heights at the ATL7 level. The main one maybe being this mean sea surface, which is derived from Ron's Cryosat-2 mean sea surface estimate over the several years of Cryosat-2 data, and some of these other corrections as well. And again, Ellen's going to talk about how, again, if you want to go back from ATL7 to ATL3, we need to kind of take these corrections back off for those heights to be, for those heights to match up. Yeah, and so this is kind of a nice example of the difference between the 2 data sets that Marco produced. So on the bottom left, we have the ATL3 photons. And above that is the equivalent ATL7 segment heights. A key thing to consider is that because we do this photon aggregation, the photon rate isn't uniform, right? A shiny reflective surface is going to have a higher photon rate than a darker, less reflective surface. So over shiny surfaces, we have high photon rates, and it takes us less time or less a long track distance to aggregate 150 photons. So that means, unfortunately, with ATL7, we have this kind of complicated variable resolution data set. There's also a difference based on the weak and the strong beams. So strong beams have around 4 times the energy of the weak beams. So again, it's going to be higher photon rates for those strong beams and shorter aggregation segment lengths. General mean segment lengths for the strong beam is around, you can think of it as around 15 meters or so, but again, there's a large spread there. And for the weak beams, it's around 60 meters. Again, roughly 4 times as large. For the actual resolution, we need to combine that segment length with the footprint resolution. So the ATL3 footprint resolution is shown on the bottom right there. So 17 by 17 meters, maybe. That number keeps kind of changing. Maybe it's 15 or 14. I'm sure Ben can correct me after this. Again, the whole idea of this aggregation is to lower the precision or vertical uncertainty. And again, that's kind of based on this idea that these errors are random. And so if we aggregate n number of photons, we can reduce our uncertainty by 1 over root n. So in this case, we go from a vertical uncertainty of around 20 centimeters down to something like 2. And that's how that 150 photon aggregation was chosen. So that's height. That kind of makes sense. But then the other thing we need to do is decide whether those height segments come from sea ice or open water. Because for sea ice, we want to know if it's either of those two surfaces to be able to derive freeboard. And so that's where things get a bit more confusing. This is a decision tree that was developed to try and do that. So this decision tree takes in 3 inputs: the photon rate, which I just briefly described, the Gaussian fit, so again, that kind of width of the Gaussian that's fit to the ATL3 photons, and the background rate. So the background rate mainly comes from the sun, again, emitting energy, some of that at the same wavelength as the Atlas sensor, but also from other things, maybe even the detector itself. Key things here: very low photon rates, that's flagged straight away as a cloud. Higher photon rates, it could be ice, it could be leads. The really high photon rates, we generally think of as potentially specular. But the way of actually deducing those is to look at the photon rate, then also look at the ratio of photon rate to background rate. I'm skipping through this very quickly because of time. It's explained in a lot more detail in the ATBD. But this is kind of an interesting point to consider. So for a surface that's very shiny and very, very smooth, such as a specular lead between ice flows, we expect that the photon rate should spike and the background rate should drop, right? The background rate is coming from a different incident angle, and we expect that to kind of scatter away from the sensor. Whereas for signal photons, we expect that to peak. Dark leads, that gets a bit more confusing. We're trying to look at low photon rates and looking at how smooth or rough the Gaussian fit is and how the background's changing. And that's kind of harder to derive. One of the things I want to point out is that some of our recent work in developing this kind of release 3 data set is our kind of increasing lack of confidence in those dark leads. So dark leads and specular leads are still included in the products, but for the new release 3 ATL10s, which I'm just going to mention in a second, we've dropped support of the dark leads in terms of deriving freeboard, partly because we saw a lot of misidentification of ice as leads. So again, that's not in the data that you're going to be using, but it's something to consider. Again, this is kind of the example of what we might see as kind of algorithm improvements and the assessments that we're trying to do in the project science office. Another thing to consider is summer data. So ISAT2 operates year round, which is great. And so we're producing data through summer, which is very exciting. Summer is obviously even harder than winter because we have melt ponds, and melt ponds are very confusing. Melt ponds kind of look like leads, but they're, on top of the ice surface instead of next to the ice floes. So currently ISAT2 doesn't really have a robust way of differentiating melt ponds from leads. Essentially, the algorithm just says, in summer, all of those things except clouds could be a melt pond. So that's the slight cop out from the algorithm there. So that's why understanding melt ponds in ISAT2 sea ice data is still very much a research topic that I know several people on this call are working on. Okay, so going from ATL7 to ATL10 sea ice freeboard, everything I just described in those previous decision tree plots are what we refer to as candidate leads or radiometric leads. So segments that essentially look like they could be a lead, but they're not necessarily used as a lead tie point in determining freeboard. Those segments have to pass a final test. And that test is this height percentile threshold. So this is essentially to make sure that there isn't misidentified ice segments going into our sea surface determination. So all this test does is basically look at the height and make sure it's in the lowest 2 percentile of a local 10-kilometer height distribution. You can imagine that for the summer data, that's maybe even more important, right? Because we can have maybe melt ponds that look like leads, but then the hope here is that this kind of height threshold can catch some of those and discard them and only keep the lower height elevation leads if we want to try and derive freeboard in summer. So after that, this kind of mean local sea surface is then derived, and freeboard is then calculated just by differencing the heights from that sea surface. So yeah, most of what happens is in ATL7. ATL10 is this kind of final step to then derive freeboard. There's a couple of other things that happen. There's some kind of quality flagging, looking at how good that Gaussian fit is. Some quality numbers assigned, and some of the bad quality height segments are thrown out in the ATL10 freeboard data set. So that's something to consider. And again, we've changed that in release 3. So we've kind of loosened that restriction to enable some of the lower quality height segments to pass through. And then the other thing to consider is the filtering. So in ATL7, we include everything above 15% concentration from passive microwave data. Whereas for ATL10, that increases to 50% because we're worried about things like waves in the marginal ice zone impacting our freeboards. And we also introduced this coastal mask because we know that it can be hard to determine a decent sea surface estimate in coastal regions. How am I doing for time, Anthony?
I think it's time to wrap up.
Okay. Well, good. I don't have too much more to say. I did want to just show a nice example that we've been working on validating this ATL7 data set. So this is a nice figure that Marco generated showing at the top is Sentinel-2 RGB image. And then the lower panels are showing information from ATL7. I'm not going to dwell on this because there's a lot here and I've run out of time, but the cool thing, if you look at those bottom panels, it highlights that idea I mentioned. We see a spike in the photon rate in the middle there and a drop in the background rate where we have what we think is this big specular lead. And we can see similar things happen to those small leads on the right as well. So yeah, a nice example of ATL7 working pretty nicely. This is for a scene in May in the Lincoln Sea. ATL10 also looking pretty good. The freeboard distributions, yeah, make a lot of sense. And again, there's been some work ongoing to verify those with Operation Icebridge data. Yeah, there's been some work ongoing to then derive sea ice thickness. I'm going to talk about this more in the tutorial on Tuesday, and that might extend into the Wednesday advanced topics as well. Again, how we can go from ATL10 to then maybe deriving our own sea ice thickness estimate. I've just given a very brief example in those notebooks, but also wanted to point you to this alternative method that's been developed as well to derive thickness by differencing cryosat-2 radar freeboards from ISAT-2 freeboards, which is pretty cool. So I'd recommend giving that paper a read as well. This is the final slide, I promise. I wanted to just make you guys aware of some issues around data availability and potential pitfalls. I really want to stress this idea that you should read the known issues document that is posted on the NSIDC website. It's updated for every release and is a good resource for highlighting things you might want to consider when using the data. Another issue we wanted to flag was there's actually like 3 different freeboard variables in the freeboard data set, which is pretty confusing. There's different ways that we can derive a sea surface. One of those is using all of the beams together, which is called this kind of swath freeboard product. The beams aren't fully aligned right now, though. I think that's already been mentioned in some of the intro talks. So we don't trust that data product right now. And that's been actually removed from the release 3 data, but I think it might still be in the release 2 data sets. So that's something, again, to consider. And maybe I can expand on that more in the chat. As I said, they have variable along track resolutions. So that's something else to consider when you're doing any statistical analyses of the data. And there are also lots of gaps. So don't assume that this is a nice, consistent data set. And that's all I've got. Yeah, ISAT2 is looking great. The CI's data is looking great, but things are always changing and improving. So yeah, kind of watch this space. Thank you.
Great, thank you, Alec. Let's thank Alec for a great tutorial, and we'll ask Ben Smith to get his setup as we transition over.
Can I stop sharing my sheet?
Yeah, if you could stop sharing.
Okay. So let's get this going in presentation mode. So thanks, Alec, for giving us a good introduction, and to David for giving us a lot of great tutorials this morning. I'll be digesting that over the next, I don't know, 2-3 years. I'm going to give you what the land ice products are looking like right now. And I'm going to be focusing sort of on the idea of making repeat track measurements with land ice products, because the product that I've worked the most on, ATL06, is designed specifically to allow elevation differencing. So we'll talk about the pitfalls of doing that right now and what's working well. I'll talk about the general scheme for generating ATL06, and I'll talk about the corrections that we have to apply to try and get sub-centimeter accuracy that would allow us to do the really fine scale differencing we want to be able to do over the Antarctic plateau eventually. And then I'll touch a little bit on ATL11, which is my current product in progress, which I think should simplify a lot of elevation change tasks going forward. So some of the stuff that we'll be talking about here is review. This is a picture of the scheme that we had in mind when we designed ISAT2 for doing repeat track differencing. ISAT1 just made repeat measurements of the same track, but it did it only with a single beam. So if you wanted to figure out the difference in height between 2 beams for a particular spot on the surface, you had to contend with the fact that you didn't necessarily know the surface slope. Surface slopes could look like elevation changes. With ISAT2, we're measuring for each of those 3 beam pairs, we're measuring 2 elevations separated by about 90 meters, and that lets you correct for that a cross-track slope. It lets you know what the cross-track slope is and infer the elevation of a common point. So we can eliminate the cross-track slope and get elevation change directly from the 4 measurements you get with 2 repeats over a particular location. Or if you have more measurements, you can try and do a better job of estimating what the surface height is. I think this is probably a review over what people have said before, and I realize that this slide is old enough that it was generated with a different aspect ratio, so all of my tracks are a little squashed. But you can see the dense tracks that you get from repeating the same measurements over and over again. At 72 degrees north, our reference tracks, our nadir tracks, are 9 kilometers apart. So if you fill those in with the 3 outrigger pairs, with the 2 outrigger pairs, you get a uniform track spacing that's converging on 3 kilometers. The individual tracks are 90 meters apart, and so given a conservative estimate of how well ISAT2 would be able to point to its repeat tracks, we'll get overlapping tracks pretty consistently. ISAT-2 has turned out to be much better than what we designed it to be. So it can make these measurements with repeat track accuracies of, in some cases, better than 10 meters. So in many cases, you just repeat the same territory over and over again, and you don't have to do a whole lot of work to get elevation differences. But we still, in some cases, need to do the correction. So I'm going to continue as if we still were not pointing that accuracy. So looking at the land ice data products, we're mostly going to be talking about ATL06, which is surface height estimates for 40 meters segments along track. We've adopted a fixed spacing in contrast to the sea ice, which uses a variable long track spacing, just so that we can always return to the same point and make the same measurement if we want to. In the right-hand column, I've given sort of a rough estimate for how many points per 10 by 10 kilometer box you might get. And this is showing that as we go down the list of products, the resolution gets worse and the number of points you have to contend with gets better and better. So if we go from a resolution of 0.7 of a meter in ATL03 to a resolution of 40 meters in ATL06 with a posting of 20 meters, we go from millions of points per year in a 10 by 10 kilometer box to tens of thousands of points per year. And then as we go to ATL 11, 14, and 15, we get to coarser resolution and fewer data points. So ATL 11, for instance, this is actually an older slide. It's now posted at 60 meters with, 60 meters, 100 meters, 20 meters along track resolution. But still, that's thousands of points in a 10 by 10 kilometer box. The reason for choosing this scale was sort of both trying to get a high enough precision per point and enough points along track to estimate the along track surface slope, while trying to resolve features at sort of a reasonable scale for a glacier. So the picture on the right is a picture of a crevasse field in Antarctica. This is a marginal crevasses that are spaced at tens of meters. The shadow on the ground is the shadow of a DC-8, which is about 50 meters long. And so you can see that despite the fact that the surface is broken up at small scales, there are areas within this crevasse field that are coherent flat surface at a scale of about 50 meters. Now, of course, we can find examples where the surface is much more broken up than this, and we can find vast, vast areas of Antarctica and Greenland where the spatial scale is much larger than this. But 50 meters seemed like a scale that resulted in a project that wasn't too horribly bulky, but was still telling us something about surface elevations at a scale that was relevant to the glacier. The structure of ATL06 is photon heights from ATL03 that are fit with these 40 meter long track segments. The segments are coordinated between beam pairs and between repeats. So if you go to the same segment number within a beam pair, you'll find the same along track location for both beams. So you can directly measure the cross track slope by taking any two of these measurements. We take photons within reduced vertical bounds. So instead of taking all the photons that are available, we take only a vertical subset of those photons and fit the segments, and we adjust those bounds to try and get a small vertical window that will give us a small amount of noise. And then we use the statistics of the residuals to estimate the errors, and we can also use the statistics of those residuals to make corrections for some instrumental and algorithmic biases that might otherwise creep in. So here's a picture of the photons that you get back from a strong beam and a weak beam from a single pulse. From a strong beam, we get back up to 12 photons. So this is them randomly distributed by the footprint pattern of Atlas. In the bottom, we have a weak pulse, which has only 3 photons, and those are also randomly distributed by the beam pattern of Atlas. If we aggregate together a 40 meter segment, this is what we get. So this is now 40 pulses, showing the pulses, the first pulses we measured with all of the rest of the 39 pulses laid on top of those. So both for the strong pulse and the weak pulse, we get a messy looking random distribution of points, but you can see that we should be able to get something coherent out of those by aggregating the, the hundreds and hundreds of points that we have for the strong beam and the weak beam. So 57 pulses go into 40 meters for ISAT2, and that's, hundreds of, a few hundred pulses, a few hundred photons for the strong beam, and a few tens of photons for the weak beam. Now, with these along track segments, so we're doing 20 meter overlapping segments, we're doing posting at 20 meters, so we're overlapping the 40 meter segments by 50%. The segment numbers coordinate between beams in a pair, as I mentioned already, and the along track coordinate system lets us measure both the along track slope and the across track slope. So there's repeat measurements. This is a picture of the schematic for doing one of these measurements in ATL06. This is now a plot, Z being the direction and X being the along track coordinate. So we take all the points within 20 meters on either side of the reference track. We fit a line segment to those points, and then we iteratively shrink the window to try and converge on something that looks like an ice sheet surface. So you can see that there are background photons distributed around the surface itself. We try and ignore those background photons and just take the photons that are at the surface itself. We do this with an iterative fitting strategy that I'll show in the next slide. This is an animation, and if we can get it to play, it's going to show iterative fitting of a weak beam signal that's been attenuated by clouds. We use the photon classification from ATL03 to give us a first guess at where the surface is, and then do an iterative technique to try and shrink down beyond that. So let's watch this run. So we start out considering all the photons as possibly being ground, and then we iterate to try and reduce that. This first attempt doesn't work very well. Let's try the next one. Let's see how this goes. Sorry, let's look at the next example. So the top example is now iterating more successfully. So this is homing in on a concentrated collection of photons that turns out to be a pretty good example of the surface. And then next I'm going to show you one that doesn't work at all. This one diverges. And this one is a good strong signal example which should converge directly on the surface without any fuss at all. Yeah, so this one we have lots of signal. We converge directly on the surface and shrink down the window to a very small size after a few iterations. So ATL06 had to be designed to consider all these possible different cases, where some cases where we have good signal to noise ratio, some cases where we have bad signal to noise ratio. It's designed to return an answer whether the data are good or whether the data are bad. So when you look at the ATL06 product, you'll see a mixture of very good looking segments and some segments that are clearly not anywhere near the surface. We were fairly conservative about deciding to include segments even if they're not very good, because we didn't know in advance what was going to be successful and what was not going to be successful. But we provide a lot of metadata fields that let you winnow down the good segments and just identify the ones that are going to work for you. So let's go on to the next example. Here's an example of an ATL03 photon cloud with ATL06 elevations laid over the top. We have some areas of smooth surface where everything worked extremely well. The ATL06 segments have a good description of what the surface looked like. We come into more rifted or crevassed areas, and we see that, yes, definitely the ATL06 segments are showing you what the surface looks like. There may be more details that would be relevant to some analyses. But we're still returning something that characterizes the surface height. And if the surface is changing enough, then we can get an estimate of how the surface has changed over time. A few complications in this. One of them is that not all the photons that you detect from the surface have taken a direct path from the satellite to the surface and back. So you can have cases where a photon comes and hits a cloud, is diffracted by particles in the cloud off to the side, still returns to the field of view of the instrument, and then comes back to the satellite. If you have an instrument with a wide field of view that can see photons in a wide area around the spot that's illuminated by the laser, you can have photons that are scattered through a rather large angle and then return to the detector. And those can be delayed by quite a long time before they get back to the satellite. That results in a bias in those photons because they've traveled a larger distance than photons that would have gone straight to the surface and back. And so those are cases where the surface height estimate that you get back from an aggregation of photons can be wrong. It can be too low. So we have provided some statistics on the products that would help you identify those. These are usually small biases in the surface heights that you might not be able to identify just by looking at the statistics of the heights themselves. So we do provide some parameters that describe the cloud situation that would help you avoid using those in sensitive estimates of elevation change. So in a more broad sense, we provide some statistics that would help you filter out signal finding blunders from real detections of the ice sheet surface. These are aggregated into a parameter that we call ATL06 quality summary. So if we put together a number of parameters that come up with an ATL06 quality summary that's either 0 for segments that have passed all of their tests or 1 for segments that have failed 1 or more tests. So in the next couple of slides, I'm going to show how well these tests work based on simulated data, which I think gives you an idea of under what circumstances you would or would not trust the ATL06 elevations. Just looking at the product structure itself, we have, this is in a tree view, we have a metadata group and ancillary data group that tells you things like what orbit you're on, what cycle, how the instrument was configured, that sort of thing. And then we have 6 groups that give the parameters for each Atlas beam. So GT1L is the left beam in the leftmost pair, GT2L is the left beam in the center pair, GT3L is the left beam in the right pair, and then sort of labeled left and right within that. So if you go into one of these groups, you see land ice segments, residual histogram, and segment quality. The land ice segments is the group that tells you most directly about altimetry. And if you look in that group, you see a mixture of data sets and subgroups. The data sets are things like latitude, longitude, delta time, and the ATL06 quality summary, which is our estimate of, is this most likely to be a usable segment or not? It also includes the error estimates. So in general, the easiest thing to do is to just read the parameters from within each of these GT1L or GT1R groups. If you need more parameters to give you an estimate of how well things are working, you can delve into the subgroups here, which will provide the corrections that have been applied, provide things like the DEMs, provide the slopes that go along with the segment heights. So this slide shows an analysis that we presented in a paper that came out last year that shows simulated results where we generated a bunch of simulated data and then applied the ATL06 algorithm to it. And so sometimes the ATL06 algorithm found the surface, sometimes it made a blunder. The question that we were trying to address was how many blunders would we get if we filtered the data using the ATL06 quality summary? So if we had no roughness, so if we had a nice smooth flat surface and we had between 10 megahertz background rate and 0 megahertz background rate. And we had between 0.1 signal photons per pulse and 3 signal photons per pulse. What was the probability of getting a blunder? So if we applied no filtering and we had a strong signal, we were very unlikely to get a blunder. If we had a weak signal, applied no filtering, then we were very likely to get a blunder. If we used a parameter that assumed that we wanted less than 5% blunders, we could get down to less than 5% blunders. If we specified a flag that got us down to 2% blunders, we could get down to the number of blunders we expected. So we were able to use our filtering flags successfully in the simulation to eliminate most of the blunders, but for weak signals and for large roughness, there's still some that's somewhat inevitable. So the things to watch out for are large background rates and weak signals during blunder detection may not work as well. In this slide, in this picture, we're showing the accuracy, so the RMS accuracy of the signal detection. Oh dear, we seem to be getting into unstable internet connection, unstable internet here. So let me know if we've got a problem. I'm going to exit full screen here. Can I get some feedback on Slack if my connection is falling apart?
You've been breaking up a bit, Ben, but I think we're okay. It's a bit laggy. Can you hear it?
I'm going to return to the piece. We've tested the algorithm. The errors are pretty much where we expect them to be, and they're dependent on the background rate and the roughness. So to get highly accurate elevation estimates from ATL06, we have to account for some of the problems that are inherent in photon counting. So one of them is that Atlas uses an array of single photon counting channels to detect the beam coming back from the surface. So each of these channels is able to detect one photon every 3 nanoseconds. So every roughly 45 centimeters. And the photons can come back much closer together in space than that, or much closer together in time than that. And so if we didn't do anything about this, the natural result would be that Atlas would detect the photons that came back early in the return and would not detect the photons that came back late in the returns. The thing that we've done in the design of Atlas to correct for this problem was to have this array of detectors. So each detector is on average likely to get hit by about 0.7 photons from each return, from a strong return from the surface. And so that means that it's somewhat unlikely that each detector gets hit by more than one photon. But if the photons come in very quickly, or just by random chance, even if the probability of getting hit by more than one photon is low, it still happens. And that can bias the mean elevations high for strong signal cases with moderate amounts of surface roughness. So we've put together a correction that we call the first photon bias correction that uses a model of the detector to correct for problems of this type. ATL06 has its own version of this that is somewhat independent of the shape of the return pulse. We have a plot here that shows how well this works, and it shows that under most conditions we can reduce the biases due to this from maybe 3 or 4 centimeters in the worst case to sub-centimeter in the worst case. And we can also correct for the reflectance error that comes along with this. Other products have their own way of doing this, and there's a standard product that I think is on ATL03 as well that lets you do this. But this is one of the things that gets applied by default to ATL06 elevations. Another correction that we apply is one where we take into account the fact that we're estimating surface heights from a subset of all the photons that are coming back. So we're windowing our returns around the surface. If you window your return, you're chopping off a tail of photons that apparently come from below the surface. And so this correction takes into account how rough the surface is and the number of photons we've gotten back and the height of the window around the surface that we've taken. And this is also something that can be a centimeter size error, and then we can correct it down to the sub-centimeter size. So looking at how well this has all worked, we have a couple of ground truth examples. We can take ground truth by comparing laser altimetry measurements along the 88 degrees south pole hole with ISAT-2 measurements. So this is the 88 degree arc in Antarctica. And we have a scanning laser altimeter flight that went along that. And we can difference the airborne laser altimetry measurements from the spaceborne laser altimetry measurements and make a plot of that. And I've plotted these with the worst measurements laid over the best measurements. If we then break this out into along track coordinates relative to the airborne laser altimetry swath, you can see that we've got a few outlying bad measurements, a few outlying bad tracks, but most of our measurements, most of our differences are clustered around 0, indicating pretty good statistics. Now, as a warning to all of you looking at I guess the thing to point out here is that there are these outlying tracks, and those have mostly been filtered out of the data that any of you will be getting from NSIDC. So this is something that we on the science team looked at and realized that there were some tracks that hadn't worked very well. And mostly we've removed those from the data set that's been released. If we look at the statistics of these, we get median per track differences that are a few tenths of centimeters, and that's actually mostly due to a small bias in the scanning laser altimetry measurements. The thing to look here is the sigma, so the standard deviation of these measurements, and those are all on the order of a few centimeters. So per track, we're getting centimeter levels, and longer along track averages could do better than that. We've also got a traverse that we send out basically every year to measure elevations along the pole hole using GPS. And if we compare those to ATL06, we get a cloud of elevations. These are based on much shorter segments of ATL06 data, so their statistics are a little bit worse. But we're getting aggregates on the order of, so these are now in centimeters, we're getting biases by comparing all of the elevations between the GPS and ATL06 on the order of 1/4 of a centimeter the first time we did this, half a centimeter the second time we did this, and standard errors on the order of a centimeter. So I think that this is working extremely well. As I mentioned in my talk at the beginning of the week, the along track pointing is something that we got working after a couple of cycles of data. So at the top, we have the along track coordinate for the center beam. So the YATC for GT2L, which should be a number that's like 45 meters. For cycles 1 and 2, that was all over the place because ISAT-2 was not pointing at the ground tracks accurately. Once we got to cycle 3, we started nailing it. We started getting that pretty consistently at 45 meters. There are a few measurements that were used for calibration purposes where the satellite was deliberately pointing away from the ground track, and those have large values. And we call those round the world scans. And those are something to be aware of when you're looking at data. They don't come up all that often. You can see that they're geographically constrained. But every once in a while, you'll see measurements that are way off to the side from the repeat track. And that's usually what was going on. Those are significantly less accurate than the other measurements. If we look at the track distribution by cycle, cycles 1 and 2 were measured not on the repeat tracks. You can see that those are messy. They don't repeat in a consistent pattern. When we get beyond cycle 3, we get this regular assortment of tracks. So I'm just plotting plotting the nadir tracks here. But you can see that those become regular. If you zoom in, you can see that there are multiple labels for the same track. So 1346 here appears twice. When we get to cycles 3 and beyond, we only have one label for that because they're always in the same position on the ground. So this finally lets us make repeat track measurements. So here are multiple repeats for a track in Greenland. You can see when we zoom in on this, we're hitting the same spot over and over again in a repeatable way. If we zoom in, you can see this is probably a location where there was a superglacial lake that may have drained between cycle 3 and later cycles and then partially refilled. There are some small inaccuracies in our repeat track pointing, so we're not necessarily getting consistent elevations here, but if you use both beams, you can do much better and start getting at real elevation differences. ATL11 is the product that is going to address the repeat track pointing problem. I'm going to motor through the slides here a little bit because I suspect that I'm running out of time. ATL11 takes the multiple repeat tracks, infers a consistent surface that corrects the elevation from those tracks back to a reference location. And then it gives you, for a series of reference points, the time and the elevation, as well as the location of the reference point. So we'll get eventually 4.4 repeats per year out of ATL11. We'll be able to make elevation differences with this. So there's a flow chart for how this works. This corrects the elevations for that track that I showed before. The corrections are not particularly visible here, but if we take a messier example, this is now ATL11 elevation differences corrected to the same point for a pass over Jakobshavn Glacier. We can see the difference between a variety of tracks, and we can see the differences between repeats between cycle 3 and cycle 7 and cycle 3. We can see that the surface has dropped consistently by about 20 centimeters, and then in the fast thinning part of Jakobshavn Glacier, we can see a drastic drop of up to 20 meters that happened over the summer of 2019. We can use this product for doing maps of the whole ice sheet. So this is a map of the elevation drawdown for 2019 between spring and summer. And you can see these drastic drops of 3+ meters around the marginal zones. Unfortunately, cycle 4 was a cycle that didn't work as well as some of the other cycles. We had the instrument reset, and it took a little while to get it working again. So cycle 4 is a little spotty, but if you look at the difference between cycles 5 and 6, you can see that we have very dense measurements from this. And there's some differences among the elevation change measurements, which has to do with where in the cycle the measurements were taken. So ATL11 will be a product that we hope to get out later this summer. We've got the algorithm coded in Python, and that's available, although it's not set up to be particularly friendly to use right now. But we're expecting to have our first release of this later on this summer, depending on how fast we can work through some metadata issues with NSIDC. So thanks a lot for bearing with a somewhat long and scattered talk.
Me okay?
Yeah, we can hear you.
All right. So I just posted in the general channel for our sort of quick sort of introduction into data access, and try to do a quick exercise using open altimetry. The notebook that we have is a part of the data access. We have a larger data access repository on the ICET2 GitHub site. No need to clone it. Feel free if you kind of used to that workflow and ready to go. But I did post a link to it's actually the NB viewer site to just for kind of easy access to kind of reading it, because this intro notebook is really 95% markdown. It's really meant to be sort of a documentation kind of resource for you. I have a lot of different links and various explanation of different discovery and access methods that I'm going to walk through. So I have my Jupyter Lab instance open right now, and I'll kind of follow along there. But again, just feel free to use that, that NB viewer link, and those links should be live and work. So if you want to kind of play along and follow along and click through the hyperlinks, feel free. You might have to kind of force those links to open a new tab, but feel free to kind of go from there. So hopefully you guys are all on that page, but again, you can just kind of follow along. So this is sort of, again, it's sort of a part one as far as, you know, ISAT2 data discovery, visualization, and access resources. And Jessica Scheich and I have been working together on these. We have a couple of different notebooks, and we'll be presenting and actually working hands-on using the IcePix tool on Monday to actually access the data. So, but this is, again, more of just an exploration and kind of an introduction. So there is, I'm kind of going to mainly just walk through this very pretty busy diagram here on the sort of mechanisms available for ISAT2 data exploration. And first, I did just want to introduce where I'm at in my background. I work at the National Snow and Ice Data Center at the NSIDC, and I am on the DAC program. So we are one of 12 NASA DACs, or Distributed Active Archive Centers. So I work on sort of our data services, data access and service tools, sort of across the DAC, but with a lot of focus on ISAT2. I've worked for a couple of years on ISAT2 support, and we have several other people at NSIDC I know that are attending the Hack Week as well. So as far as data discovery and access, this actually came about, this diagram came about from some conversations that Jessica and I had months ago, and I want to give her credit for actually producing this diagram. And it really came about with us just trying to kind of discuss and walk through all of the different mechanisms that we have. So, you know, as several instructors have already talked about, you know, the data are available through NSIDC, but we are, again, we're part of the larger kind of NASA Earth data sort of system. And so there's also sort of those larger NASA systems where you can access and search for data. There are things like open altimetry that we'll look through in just a moment, which is a collaborative project with NSIDC and others at Scripps and UNAVCO and San Diego Supercomputer Center. And then there's community developed tools as well. So that's what we'll talk about much more on Monday that Jessica has been leading as far as IcePix. So there's a couple ways to slice this diagram. So there's, you know, kind of walking from left to right, there's sort of, you know, data discovery. So that's really just sort of the search options, the visualization options prior to actually getting your hands on the data. Then there's actually the access component. I'll speak to this in a little more detail in a minute. Then there's sort of that next step of, well, okay, I want to access the data, but now I actually want to read it in, and what are the methods to do that? And then there's sort of the rest of the workflow, which is, of course, you know, what you've been working on, what you'll be working on through the projects this, you know, next week. And then kind of going from top to bottom, you know, there's web-based resources. There's lots of tools out there that are on the web through web user interfaces. And then there's programmatic methods. So, you know, things, if you are familiar, have used APIs before, which are application programming interfaces for both discovery and access. There's sort of these underlying programmatic methods that in a lot of ways power the web-based options as well. So you see all of these different arrows and they're color-coded. So kind of there's, you know, black arrow that's kind of demonstrating kind of the open altimetry workflow from data discovery to access, and as well as sort of the NSIDC and NASA Earth data methods. And again, there's sort of those underlying programmatic methods using APIs and other sort of tools and wrappers. And you can see that these arrows all connect. So, you know, there's, you know, another thing I want to point out, and I know there's been some intro on this. Obviously, we've had some great tutorials on Jupyter, and there's some introduction to Pangeo as well. And so the Pangeo community and sort of Pangeo ecosystem is, you know, obviously promoting these sort of community-based and open sourced sort of tools to provide a comprehensive ecosystem for data discovery and access. And it's an exciting time right now, especially as data are sort of in this process of moving a lot of data to cloud-based resources, which we're in the process of doing right now for ISAT-2. You know, Pangeo is really paving the way as far as, you know, optimizing, you know, sort of these very, you know, compute resource intensive methods that are needed to access such large data sets. So that's a really large overview right now. And I know I kind of want to quickly go through this, but, you know, I did just want to point out and emphasize again that IcePix was really created, you know, out of the Hack Week last year. You know, after everyone would work through data access methods, we realized that, you know, there's really an opportunity for the community to get involved in really optimizing the methods for ISAT-2, and not just to discover and access data, but really to get at this, you know, kind of continuous or a single kind of method to not only discover, access, but also read the data in kind of within a Python framework, so that you can then kind of continue to do the rest of your workflow. So that's really and sort of the intro to IcePix, and hopefully a little teaser for what we'll talk about on Monday. So as far as polling questions, I know I scheduled those a little early. So you should have seen those in the questions Slack. And I know that some of you already responded, but this is hopefully to just get you thinking and brainstorming a little bit, especially as we move into the project, you know, getting into the project organization a little later this afternoon. But I first wanted to start with this, you know, simple question on, you know, have you ever heard of open altimetry? Do you use it exclusively? You're somewhere in between. So if you haven't answered that question already, you might have to scroll up a little bit on the Slack channel. Please feel free, if you never heard of this before, or if you're intimately familiar, please feel free to respond, and I'll kind of just take a look and kind of cater the next exercise to those responses. And then there's also an intentionally vague second question right under that multiple choice question on how do you prefer to search for data prior to downloading files. And this could really mean anything you want it to mean. It's really, like I said, I kind of want, you know, get you brainstorming about, surely you've already been thinking about, you know, what data or projects you're interested in, but especially as you actually start to access it, you know, within the next few days and as we gear up, you know, this may be, hey, you want to be looking at a single repeat ground track over an area, and you have a shapefile, you know, kind of something similar to maybe what David went over earlier. You kind of have an area of interest or glacier, for example, and you want to use that as your spatial search. You know, maybe this is, you're interested in searching based on seasonal date range. You're looking for data that's coincident, ISAT-2 data that's coincident with another data product. Or this could be, again, anything about that you prefer to kind of stay in Python or a different coding language versus a web interface or vice versa. So feel free to write those responses down. I might not be able to kind of specifically cater the next step to this intro session based on all of these answers, but again, it's really just to kind of get you thinking about it. I'd love to kind of take a look through even after this session, and that could help even for Monday's tutorial as well, and throughout the week. And it could also be, you know, if you've had challenges, let's say there's something you want to do and want to, you know, have a way to search for data, but you might not know of a way to do it right now. So while you're filling those out, I did just want to point out, again, I'm not going to go through all of this. This is really just meant to be sort of documentation for you throughout the week. I posted a lot of resources on the NSIDC page so that you can get to the data from the NSIDC website. So I pulled out the sea ice and land ice products that we've been talking about. You can access the data directly on NSIDC landing pages. So I have some examples there. Just scrolling through this, like I mentioned, you know, we're part of the larger NASA Earth Data, or it's the EOSDIS system. And as Jessica and I will kind of talk through a little bit more on Monday, since IcePix is basically a wrapper around the NSIDC API and the CMR API, which is the metadata repository that sort of houses metadata for ISAT-2 and all NASA Earth data. You know, we'll talk about that a little bit more, but these are just some resources there to give you an idea of how all these things connect. And I did just want to take a brief minute to mention that, and I have this link here on the NASA EOSDIS move to the cloud. and again, EOSDIS is kind of the system powering NASA Earth data. We are in sort of this migration phase, and it's actually been really great to start seeing on Slack some conversations and even project examples that revolve around, you know, sort of, again, the sort of compute intensive ideas that really might be better suited for cloud optimized formats and for data that are directly accessed in the cloud. We are moving in that direction, and kind of every sort of mission and DAC is kind of on a different schedule there. So we're sort of in that process of migration. I'm happy to answer more questions about that if you have any kind of throughout the week. We're still kind of in the sort of download paradigm. We know ISAT2 data can be really large. And again, at NSIDC DAC, we're really prioritizing ISAT2 data, knowing that it's a large data set. So that's sort of where we're at now, but I just kind of wanted to give a little bit of intro into that migration and that status. So moving into open altimetry, and actually I'll take a look at the poll results right now, and I know that Jessica's helping out as well, but it looks like we're about, you know, it seems like most people are kind of in the, I've never really used open altimetry, or I've kind of dabbled in it before. So that's great. And again, we'll take a look at the sort of open-ended question on searching for data later on, but thank you for your responses there. So open altimetry it's a really great web-based visualization platform, and you can actually also download and access the data as well through open altimetry. So as I mentioned, it's a collaborative project. There's some of us at NSIDC that have been involved, but this has been led by Adrian Borsa at Scripps, and again, the San Diego Supercomputer Center is really powering the database behind open altimetry. And what's really great about it is that you can visualize the data on the fly. You don't need to download the data ahead of time. So it's a really great tool. So what I wanted to do, again, I know we're running short on time, and I may just do a really quick introduction to open altimetry, and then have, you know, kind of allow you guys to play around with open altimetry on your own time, maybe during the break, or, you know, throughout next week. But what I thought I'd do for this exercise is I actually kind of use some inspiration from a Photon Friday. I think Tom Newman had introduced sort of the social media campaign that the ISAT2 team at NASA has been working on, where they kind of focus in on just, you know, interesting features and areas. So it was kind of fun for me to look at a focus on Pine Island Glacier from January of 2019 and kind of find that feature in open altimetry. So if you want to go ahead and click on this annotation link, what these are, and I'll actually explain annotations in just a minute, but this should take you to a predefined area that I've already sort of set up. And this is quite zoomed in. You might see just a black background initially. I think that's because we're zoomed in quite a bit. So I just want to give a quick overview of what you're looking at in open altimetry. And I'll start actually just by at the top left, you know, there's just kind of a zoom out and zoom in feature. So I'm going to zoom out a little bit, and that should actually start to display the base layer. So I think we're just a little zoomed in. So if you see that, feel free to zoom out. Again, we're over Pine Island Glacier, and you could see on in the timeline here, this is from January 15th of 2019. So open altimetry kind of does a daily, sort of a single day sort of snapshot of the data that you're looking at. And what's really nice about it as well, on the top right, my dialog box and zoom out of the way. The top right, you could see what data set is highlighted. So another thing, if you're interested in kind of looking at and comparing the level 3A surface specific data products, you know, whether it's between HL06 and 08, I know there's been some interest in some bathymetry, I think I've seen. So if you are looking in those coastal regions where, again, there's sort of surface overlap across products, you can toggle between those at the top right. You can change the projection. That's what that globe button is. And then this sort of tag icon is where you can turn on and off annotations. And so the link that you clicked on is a preset annotation that you can create. And this might be a really great thing that you might consider for your projects if you're interested in an area you can kind of share and take a snapshot of a feature of interest in open altimetry, and you can share that link publicly. So that's just one feature there. I'm not going to go over every single feature, but what's really nice, like I said, Ben and Alec gave a great intro on the sea ice and land ice products, but you can, again, really start to actually view the data. So one thing I'll point out at the top left, you may see this percentage sign, percentage indicator, and that shows just how much data are actually being viewed at the current zoom level. So it's only 1.5% right now, really small amount. So each dot is going to signify one individual segment. In this case, from ATL06, you can see the track ID, what beam you're looking at, and what product. But as you zoom in, you can start to see more and more data. So you can zoom in all the way to 100% and see every single value. Again, with ATL06, that's posted every 20 meters with that 40-meter kind of window. The other thing is that you can search. So although it's sort of a single day view, these red lines indicate what other tracks are available for different days. So it's getting a little slow right now, but you can look at all the data availability. If you click on the other tracks in red, you could toggle that on and off. You could look at there's a layer where you can look at the MODIS surface reflectance imagery. So I know, again, there's lots of features. It's pretty self-explanatory, but I did want to show the on the fly plotting feature that I think is really beneficial and pretty powerful. So on the top left, if you click on the select a region button, and you can pretty much just, in this case, you can trace the red box that I've already created. And then a little icon will pop up that says view elevation profile. And that's going to, again, plot the data on the fly. So if you're kind of trying to figure out and searching for data again, where there might be a surface feature of interest, you can do this without downloading the data first. So what you see in this next window is the elevation profile of ATL06. It'll also show you the coincident ATL08, 13 other specific, surface specific products. And then, I know Ben and Alec kind of walked through the beam structure. And that's another thing I wanted to point out back to the map view, that, and I know that I believe Tom Newman also talked about this, the spacecraft does switch orientation every 6 months or so. So this is also a nice way with open altimetry. It tells you if that beam is in the strong or weak position, depending on the orientation. So in this case, the kind of left beams represent the strong beams. So if I, just for example, look at the GT1L beam, again, this is me sort of tracking the Photon Friday features that were present. The other thing you can do is look at the coincident ATL03 photon heights, so you can also get those. I think I've probably ran, I know we're way over time at this point. Back to my notebook, I had a couple of other kind of characteristics and sort of prompts for what to look at. I want to point out also that you can open up a Jupyter notebook in Binder from that profile page. There's that launch Binder button, and that will actually utilize the Open Altimetry API. But you can look at it's kind of cool. You could see a 3D plot of the data that you've highlighted. And can I have some other questions there on just sort of detecting, in this case, you can look in that window of Pine Island Glacier and grounded ice, and also some iceberg features, which is pretty cool, again, coming from Photon Friday. So this was short. I know I went over. Thanks for everyone's patience, and just want to kind of note this was short, but please post questions in the question Slack. Of course, we'll continue with programmatic data access on Monday using ice picks. So this was sort of just a first glance at the data. If you want to really start to visualize it,